Hello students, good night to all of you. So once again welcome to your YouTube channel TKG Physics classes, and today we will discuss the conservation law of linear momentum. All of you know there are four fundamental laws of linear momentum: conservation law of charge, conservation law of energy, conservation law of linear momentum, as well as conservation law of angular momentum. Now what is the statement of conservation law of linear momentum? You see, the formula of linear momentum: a body of mass m moving with velocity v, the formula of linear momentum, that is p equal to m into v. Now conservation law of linear momentum states that if no external force act on a body, the linear momentum of the body remains constant. You see, suppose a body of mass m moving in this direction along x-axis. Now if I apply a force along this direction, obviously the linear momentum of the body will be increases, because you are applying force along the same direction where the body is moving, so its velocity increases. When velocity increases, its linear momentum increases. Now suppose we are applying a force in the opposite direction of the motion of that body, so here linear momentum will be decreases. But if no external force act on a body, in that case the linear momentum remains same. And this is our statement. Write it: when no external force act on a system, the total linear momentum of the system is conserved. Now there are several applications of conservation law of linear momentum. One important application, that is recoil of a gun. You see, this is a gun, suppose mass m, capital M, and this bullet mass small m. Initially both are in under rest condition. So what is the initial momentum? Initial momentum, velocity 0, and here velocity 0 initially. So initial momentum, write it, initial momentum, that is 0. Now when firing, after firing, suppose the bullet is moving with velocity v and the gun is moving with velocity capital V. After firing, the bullet is moving with velocity small v and the gun is moving with velocity capital V. So what is the final momentum after firing? So the final momentum after firing, that is mv plus m small v. M into capital V, this is the momentum of gun, and m into small v, this is the momentum of bullet. Now you see the linear momentum conserved. That means the initial momentum is exactly equal to the final momentum. Now you observe what happens. Initial momentum, that is exactly equal to the final momentum. Initial momentum 0 and final momentum m capital V plus m into small v. From here you can say mv, that is equal to minus mv, that is equal to m into v. From here capital V is equal to minus mv divided by m. This is the expression of capital V, and capital V is the velocity of this gun. Now see what is the significance of this negative sign. This negative sign indicates that the velocity of the gun is exactly opposite to the velocity of the bullet. That is, the gun kick a backward direction when the bullet is going in the forward direction, and this is the recoil of a gun. This is the recoil velocity of a gun. Okay, so here the gun is moving in the backward direction and bullet is moving in the forward direction, and this is based on the principle of conservation law of linear momentum. Rockets, aeroplanes, both are working on the principle of conservation law of linear momentum. Explosion of bomb is also based on the conservation law of linear momentum. So these are the applications of conservation law of linear momentum. Now in this video we will prove three theoretical part. First one, we will prove the law of conservation of linear momentum from Newton's second law of motion. Secondly, we will prove the law of conservation of linear momentum from Newton's third law of motion. And the vice one, vice versa. That is, we will prove the law of conservation law of, we will prove Newton's third law of motion from conservation law of linear momentum. Important part for your theoretical purpose. Okay, so first one, you see, we will prove the law of conservation of linear momentum from second law of motion. All of you know about the second law of motion, that is F equal to m into a. The rate of change of momentum of a body is directly proportional to force applied. Yes, okay. So at first write it. Consider a n particle system. Consider a n particles isolated system. Isolated, that means the no external force act on the body. Okay, isolated system of masses m1, m2, m3, like that, dot and finally mn. Moving with velocity, write it, moving with velocity is v1, v2, v3, dot up to vn respectively. That means we consider a n particle system and the system is isolated. That means no external force act on the system, no external parameter affect that system, that is named as isolated system, and the masses of the n particles, that is m1, m2, m3 up to dot mn, and m1 moving with velocity v1, m2 moving with velocity v2, m3 moving with velocity v3, and finally similarly mn is moving with velocity vn. You can write this one is vector form also. Velocity is a vector quantity. Okay, now you see what is the total momentum here for this n particle system. For first particle, mass m1 moving with velocity v1, so momentum is m1 v1. For second particle, mass m2 moving with velocity v2, that is m2 v2, like this, m3 v3, and finally mn vn. So this is the total momentum p. You can write this part also, p, that is equal to p1 plus p2 plus p3 plus up to pn. So this is the expression of total momentum for n particle system. Now you observe, we will prove the law of conservation of linear momentum from Newton's second law of motion. So write it, what actually we write from Newton's second law of motion. So write, according to second law of motion, according to second law of motion, F, that is equal to rate of change of momentum, F proportional to dp by dt, that you can also write that is equal, because constant k is equal to 1. Now when no external force act on the system, when no external force act, right, when no external force, that is F is equal to 0, so you can write dp by dt, this expression is 0. Now you see, if the differentiation ddx of c is equal to 0, the differentiation of constant part differentiation is 0. Here you see dp by dt is equal to 0. That means this differentiation is 0, d dt of p is 0. So obviously you can say it's p is equal to constant, because the constant part has differentiation 0. When p is equal to constant, you know the p, that is p1 plus p2 plus p3 plus dot up to pn, that is the total linear momentum of n particle system. So from here you can write that is p1 plus p2 plus p3 plus up to pn, that is equal to constant, and this is the conservation law of linear momentum, which is proved from Newton's second law of motion. You see, the total momentum remains constant. When constant? When there is no external force. And this is the statement of law of conservation of linear momentum. When no external force act, we use this one, no external force act, and in that condition we prove that the total linear momentum of the system conserved. This one, the total linear momentum of the system is conserved. And here dp by dt, that is equal to 0, and constant part has differentiation 0. Here d dt of p is equal to 0, that means p must be constant. Okay, so this is our first theory. Now we will prove the conservation law of linear momentum from Newton's third law of motion. Okay, write it. So our second part will prove conservation law of linear momentum from Newton's third law of motion. So write it at first. All of you know the third law of motion, every action has an equal and opposite reaction. So we will prove law of conservation of linear momentum from third law of motion. Okay, so this is our second derivation. Suppose a body A of mass m1 moving with velocity u1 and another body B of mass m2 moving with velocity u2 in a straight line, and you consider here u1 is greater than u2. So when these two bodies moving with the same direction with velocities u1 and u2, and here u1 is more than u2, so obviously after some time this body collides with this body, so there is a collision. Okay, write it. So after some time two bodies collide, A and B. In this direction there is a force, and in that direction there is a force. This force is named as F. You see the force on body B by A, so this is named as FBA, and this is named as FAB. During collision, body A exerted a force on body B, which is named as FBA. Similarly, body B also exerted a force on body A, which is named as FAB. Okay, and after collision, so this is the during collision. And after collision, suppose body A is moving, which mass m1 moving with velocity v1, and body B of mass m2 moving with velocity v2. So write it. First of all, we consider a system of two bodies A and B of masses m1 and m2 moving with velocities u1 and u2 in a straight line, and you consider u1 is greater than u2. So after some time the body collide, and during collision body A exerts a force on B which is directed in the x-axis. Similarly, body B also exerted a force on body A which is directed along the opposite direction. Now during collision, and this collision happens in time del t. Write it. This happens in time del t. And after collision, the body A is moving with velocity v1 and body B is moving with velocity v2. That means velocity changes. After collision, velocity changes. So this is the expression of after collision. After collision. This is before collision. Before collision. Now we will prove the law of conservation of linear momentum from third law of motion. So write it. This is the basic part. At first you write this part. Now you see if AB is exactly equal to FBA according to Newton's third law of motion. Every action has equal and opposite reaction. Here A applied force on B which is directed that side, B applied force on A which is directed the opposite direction. So this force and this force magnitude value equal but the direction opposite. So we use FAB, that is equal to minus of FBA. Now multiply this part, FAB into del T, that is equal to minus of FBA into del T. Del T is the time during which the collision happens. Okay, now you calculate impulse for FAB, impulse for force FAB. That means What is impulse? That means the change in momentum. So the impulse for force FAB, that means the change in momentum of which body, A or B? You see, this is the force on A by B. So this one is equals to change in momentum, of body A, because this is the force on A by B. Now you observe the body A initial momentum, mass m1, velocity u1. So initial momentum m1 u1 and final momentum mass m1 and velocity v1. So final momentum m1 v1. So that is equal to m1 v1 minus of m1 u1. This is the change in momentum for body A. Body A, initial velocity u1, mass m1. So initial momentum m1 u1, and this is the final m1 v1. So final minus initial, that is the change. And impulse for force, this one, that means the change in momentum. Similarly, you write impulse for FBA. Impulse for FBA. Impulse for this force, that means the formula will change in momentum of body B. Now for body B, mass m2, velocity u2, that is m2 u2 initial, mass m2, velocity v2, that is m2 v2 final, minus m2 u2, that is initial. So this is the change in momentum for body B. Now we use this condition, this one. You see here, FAB into del T, that is the impulse of body A, that is equal to minus FBA into del T, force into time interval, and this one is also impulse for body B. Now you just use this value, impulse for body A, that is equals to which one, m1 v1 minus m1 u1, that is equal to minus of impulse of body B, that is m2 v2 minus m2 u2. Now simplify. So this one is m1 v1 minus, okay, m1 v1, and here you use this one. This one is minus m2 v2. So when this one will be that side, this one will be m2 v2 plus m2 v2. Now here is minus m1 u1. So this one will be, when that side, this one will be plus m1 u1, and this minus and this minus, that is plus m2 u2. Now you observe this value. What is the meaning of this one? What is the meaning of this one? m1 u1 plus m2 u2. This is the initial momentum. Before collision, you see, before collision u1 u2 velocity, mass m1 m2. So before collision, the total initial momentum, that is m1 u1 plus m2 u2. This is the value. So this is represent the initial linear momentum before collision. And you see this one, m1 v1 plus m2 v2 after collision. First body mass m1, velocity v1, second body mass m2, velocity v2. So after collision, total linear momentum, that is m1 v1 plus m2 v2. So this is the expression of linear momentum after collision, and this is the expression of linear momentum before the collision. Write it. So we can write total linear momentum before collision is equal to total linear momentum after collision. So what is the meaning of this sentence? Momentum changes or remains constant. Before collision linear momentum is exactly equal to the after collision linear momentum. That means the momentum remains constant. That is the conservation law of linear momentum. Here we will prove conservation law of linear momentum with the help of Newton's third law of motion. You see our starting point, that is FAB is equal to minus of FBA. This is the third law of motion, and from this third law of motion we will prove that the total linear momentum before collision is exactly equal to total linear momentum after collision. Okay, now third case, our third theory. Okay, so in third theory we will prove that law of Newton's third law of motion, we will prove Newton's third law of motion from conservation law of linear momentum. Newton's third law of motion will prove third law of motion from conservation of linear momentum. You see, same thing, you consider a system of two bodies m1 and m2, two bodies A and B of mass m1 and m2 moving with velocity u1 and u2 in a straight line. Here u1 is greater than u2. Now obviously after some time there is a collision, and after collision the velocity of two bodies changes. You just observe just previous case. After collision the velocities of two bodies A and B, that is becomes v1 and v2. So after collision, when velocity changes, obviously there is a change of momentum for two bodies after collision. So write it, if del p1 and del p2 are the changes in momentum, of two bodies A and B after collision, and you see, if there is no external force the conservation law of linear momentum states that if there is no external force, the total linear momentum, that is change in linear momentum, is 0. So we will prove Newton's third law of motion from conservation law of linear momentum. So write it, according to conservation law of linear momentum, according to conservation law of linear momentum, if no external force acts, the total change in momentum, that is 0. So here first body change of momentum is represented as del p1, second body change of momentum del p2, that is equal to 0, because no external force acts according to conservation law of linear momentum. Now so from here you can write del p1 vector is equal to minus of del p2 vector. Now divide both sides by del t. Now you observe this one is del p1 by del t, that is the change of momentum of first body. So write it, change of momentum of mass m1 first body, and that is equal to, this is the change of momentum of second body, so minus of change of momentum of mass m2. So the change of momentum, the rate of change of momentum, that is the force. So this one is force of mass m1 and this one is minus of force of mass m2, force of mass m1, that means this one is represented as F1, and this force for mass m1, obviously this one is due to 2, that is equal to minus of this one is force of mass m2 due to mass 1, that is F12 is equal to minus of F21. If this is the action, so this one is the reaction, that is action is equal to minus of reaction, and this is the Newton's third law of motion. So we will prove that Newton's third law of motion from the conservation law of linear momentum. Okay, so this is all about theoretical part. This is all about the today lecture. Okay, now we will check 2 or 3 numericals related to conservation law of linear momentum. Okay, chalo. See problem 1. In problem 1, given that a car of mass 1000 kg traveling at 32 meter per second, and it collide with a truck of mass 8000 kg moving in the same direction. Both are moving in the same direction and with a velocity of 4 meter per second. That is the car velocity 32, that is the initial velocity, and the truck initial velocity, that is 4 meter per second. Write it. So for problem 1, for car mass, suppose for car mass is represented as m1, that is 1000 given. Okay, initial velocity u1 given 32 meter per second. Now write for truck. For truck, suppose this mass is represented as m2, that is given 8000, and initial velocity, that is given 4 meter per second. Both are moving in the same direction. Car has higher velocity, u1 is greater than u2, that's why there is a collision. Now see, after collision the car bounds with a velocity of 8 meter per second. The car velocity, the direction of car changes. If the car is going that direction, after collision it bounds. So v1, suppose v1 is the velocity of car after collision, and here v1 value given 8, but this one is the opposite direction, so here you have to use negative sign, and you have to find out what is the velocity of the truck after that impact. After collision you have to find out the velocity of truck, that is you have to find out velocity of v2. So all of this thing you know, you just apply the law of conservation of linear momentum. The law of conservation of linear momentum says that the total momentum before collision is exactly equal to the total momentum after collision. So according to law of conservation of linear momentum, before collision, momentum before collision is equal to momentum after collision. Now before collision momentum, that is m1 u1 plus m2 u2, and after collision that is m1 v1 plus of m2 v2. Now putting the value of m1, that is 1000, putting the value of u1, that is 32, plus m2 value given 8000, and u2 value given, that is 4, that is equal to m1 value, that is 1000, v1 value given, that is minus 8, plus of m2 value given, that is 800, and you have to find out v2. So calculate it. This one is 3200 plus this one is also 43200, and this one is negative minus 8 into 1000, that is minus 8000. So when this one will be left hand side, that is plus 8000, that is 8000 into v2. So 32 64 plus 8, that is 72. So this one is 7200, that is equal to 8000 into v2. So from here the value of v2 will be v2, that is equal to 7200 divided by 8000, that is 9 meter per second. Okay, so these types of problem you have to use the conservation law of linear momentum. Now observe problem 2. Problem 2 is quite important. A body of mass 1 kg initially at rest explodes and breaks into 3 fragments of masses 1:3:3. they explode and divided into 3 segments, and the ratio given, that is 1:3:3, but the total mass, that is 1 kg. Now the two pieces of equal mass, which one, that is 1:1, fly off perpendicular to each other with velocity 30 meters per second each. Now equal pieces moving with perpendicular direction. Okay, make a diagram for it. So now for problem 2. Problem 2 looks like this one. Yes, suppose equal masses, this body and there is another body, this one is moving perpendicular. This one is the direction for first body, and for second body the direction is this one, and this is the horizontal line. This is suppose, okay, at first you write the total mass, 3 segments but total mass 1, so we can write m1 plus m2 plus m3, that is equal to 1 kg. Now see the ratio given, 1:3:3, that means m1 that is equal to m2, that is will be 0.2 each, and m3 will be 0.6. That's why you see 0.2 plus 0.2 plus 0.6, total 1 kg. Okay, so m1 m2 mass 0.2 kg and m3 mass 0.6 kg. Now two pieces of equal mass, that means m1 and m2. Suppose this one of body of mass m1 and this body of mass m2 moving with velocity 30 meters per second. Suppose this velocity is v, or you can write v1. Okay, suppose this one is v1, so moving with velocity v1 in that direction, so momentum will be, you see, m1 v1 in that direction. Suppose this one is make an angle theta with the horizontal line, so m1 v1 has two component. This component will be m1 v1, this angle is 45 obviously, and this angle is also 45, that's why both are perpendicular, 45 plus 45, that is total angle 90. So this one component will be m1 v1 cos 45, and this component will be mv is directed in that direction, so it has two component, one horizontal component that is along x-axis, that is m1 v1 cos 45, and the vertical component, that is m1 v1 sin 45. In same way you can say, you see, for second body moving with velocity v1, same velocity, same, both are velocity moving with 30, so here momentum, that means m2 v1. So m2 v1 makes an angle theta also with horizontal, so it has horizontal component, that is m2 v1 cos 45, and this vertical component will be m2 v1 sin 45. And suppose this is obviously m3 and this is moving in that direction with velocity v3. Now you apply conservation law of linear momentum in horizontal direction. You just consider the horizontal direction. Okay, so m3 mass moving with velocity v3, so in horizontal direction the momentum will be m3 v3. This is the horizontal direction, this is the opposite side, exactly equal to the forward side. This horizontal direction has momentum, this one you see, for mass m1 momentum m1 v1 cos 45, for mass m2 momentum, that is m2 v1 cos 45, both are in the horizontal direction, that is the forward, and this is the reverse. So forward momentum exactly equal to the reverse momentum, so this one will be m1 v1 cos 45 plus of, sorry, this one is m2 v1 cos 45. Now just putting the value, m3 value 0.6, you have to find out the velocity of heavier fragment, that is v3, m1 that is 0.2, v30 cos 45 1 by root 2 plus m2 that is also 0.2 30, and this one is 1 by root 2. So v3 that is equal to, you see, this one is 2 into 0.2 into 30 plus 1 by root 2, and this value will be divided by 0.6. Okay, now you can simplify this value and you will be get the answer, that is the value of V3. So here you have to consider the compare momentum in horizontal direction. So in these types of problem is important, students. So today I am ending here. Bye bye.